Okay. So, next topic in thermodynamics is mixture of gases. So, what is the meaning of mixture of gases? For example, I take a container, fixed container, and in this container there are two types of gases. For example, you can take hydrogen gas mixed with helium gas or neon gas, two types of gases, which doesn't react with each other. If they react with each other, then we have to go into chemistry. In physics, they are not reacting with each other. For example, let us take hydrogen gas and helium gas. Both of them, they are mixed with each other. So for this mixture of gases, I want to calculate their combined molecular mass. And also I want to calculate their Cp values and Cv values of total mixture. Are you able to understand? Gases individually, they have Cp and Cv values, no? But I want to calculate the Cp and Cv values of total mixture. Are you able to understand? So let us see. So what we need to calculate? We need to calculate, molecular mass of mixture. Also I want to calculate Cp of mixture, and I want to calculate Cv of mixture. So these values I need to calculate. Are you able to understand, ma? So first let us take gas number 1. For gas number 1, what we have, let us consider its molecular mass is m1. And let us consider the number of moles are n1. Similarly, Cp value is Cp1, Cv value is Cv1. I can calculate like this, no? Are you able to understand, ma? Similarly, I will take gas number 2. Gas number 2, molecular mass is m2. So, number of moles are n2, Cp2 and Cv2. These are the values. Are you able to understand? So, first of all, let us calculate molecular mass of total mixture. Molecular mass of mixture I need to calculate. So, see. So, Sima, how can I calculate number of moles? Number of moles is equals to total mass divided by molecular mass number. This is the method of calculating total number of moles, no? So, Sima. So, therefore, number of moles I can calculate by this formula. N is equals to total mass divided by molecular mass. So, therefore, total mass of gas, or I can say total mass of mixture, is equals to mass of first gas. Mass of first gas is m1, mass of second gas is m2. That's all, Nama. So can I write total mass of the mixture is nothing but m1 plus m2? I can write, Nama. Total mass of the mixture is m1 plus m2. And total mass, how I can write? Total mass can be written as number of moles multiplied by molecular mass, Nama. This is how I have to write, no? Total mass of the mixture, total mass is equals to n multiplied by capital M. So therefore, if I take for the total mixture, how can I write? Total number of moles, n1 plus n2 only, no? N is number of moles only, no? How many number of moles are there? n1 plus n2. n1 is the moles of first gas, n2 is the moles of second gas, n1 plus n2. And for total gas, molecular mass I can take m of mixture. Are you able to understand what we are writing? Gases individually, they have molecular masses, but I am taking molecular mass of total mixture. Which is represented by m mixture. So instead of total mass of mixture, this equation I can write. Are you able to understand? So this is equals to, what is the mass of first gas? Mass of first gas, number of moles of first gas is n1 and its molecular mass is m1. That is how we write now. Similarly, what is the mass of second gas? n2 multiplied by m2. Are you able to understand what is happening? So therefore, molecular mass of mixture, how can I calculate? It is n1 m1 plus n2 m2 divided by n1 plus n2. Ma? So this is the method of calculating molecular mass of total mixture. So not only for two gases, you can use this relation for calculating for any number of gases. 2 gases, 3 gases, 4 gases, 5 gases, any number of gases. Are you able to understand the formula? n1 m1 plus n2 m2 divided by n1 plus m2. In chemistry, capital M indicates molarity. Here capital M indicates molecular mass of a gas. Understood, no? So right. So what is small m? Small m is total mass of gas. Ma? Capital M is molecular mass of gas. Understood, Nama? Right. Okay, ma. So this is the method of calculating molecular mass of the total mixture, ma. Okay. Now I want to calculate Cp and Cv values of total mixture, ma. Individually I know, no? If it is a monoatomic gas, it is 3R by 2. Diatomic gas, 5R by 2. Okay, ma. If it is a triatomic gas, it is 3R. All these Cp and Cv values we know. But I want to calculate Cp and Cv values of mixture of gases. Okay. So Cv of mixture. Okay, ma. So this I want to calculate by using law of conservation of energy, ma. Law of conservation of energy. Okay. So what is law of conservation of energy? Total energy is always a constant, no? Total energy of the system always remains constant. So therefore I will write total energy of mixture. Total energy of mixture is equal to energy of first gas plus energy of second gas. Are you able to understand, ma? Total energy of the mixture I can write like this, no, ma? So it is just the addition of energy of first gas plus energy of second gas. So energy is nothing but internal energy only, no? Energy ante mani? Energy is nothing but internal energy of a gas. And yesterday only we studied what the formula for internal energy, no, ma? What is the formula for internal energy? NCV delta T. Okay. And the total energy, how I can write? I can write NCV of mixture multiplied by T. This is how I can write, no? Where N is the total number of moles. Or instead of N you can write N1 plus N2 also. N1 plus N2. Are you able to understand, ma? So energy of mixture is nothing but internal energy of the gas. Internal energy of the mixture. Internal energy formula NCVT. CV which CV? CV of total mixture. Because now I am considering this mixture of gases to be one single gas, whose CV value is CV of mixture. So this is equals to, what is the energy of first gas, ma? N1 CV1 multiplied by T. That's all, no? Internal energy NCVT. Energy of second gas N2 CV2 multiplied by T. Okay. So therefore what is CV of the mixture? CV of the mixture is nothing but N1 CV1 T. T values I can cancel, no, ma? I can remove this T values. So N1 CV1 plus N2 CV2 divided by N1 plus N2. So this is the CV value of total mixture. Understood, no, ma? Class mein hu main. Okay, ma. Now see. So CV of mixture we have calculated, no, ma? This formula you can use for any number of gases, ma. Not only 2 gases, 3, 4, 5, any number of gases you can use. Okay, now see. CV1, CV2. This is the CV of first gas, this is the CV of second gas. Okay. Now see, ma, CV value already we have written in terms of degrees of freedom. No? Do you remember what is the formula? FR by 2. Clear, no, ma? So CV is equals to FR divided by 2. This is one formula. In terms of what? In terms of degrees of freedom. Similarly, CV value also we have written in terms of adiabatic constant also. No? Huh? See what is the formula of that? CV value in terms of adiabatic constant. R divided by gamma minus 1. This is the formula, no, ma? Do you remember? So CV can be written in terms of degrees of freedom. CV can be written in terms of adiabatic constant also. Okay. Now therefore, these values I want to substitute in this equation so that I can calculate gamma of the mixture also. So what I want to calculate now? I want to calculate gamma of the mixture. What is meant by gamma of the mixture, ma? Gamma of the mixture means what? Adiabatic constant of a mixture. Are you able to understand? So therefore, instead of CV of mixture, what I can write? I can write R divided by gamma of mixture minus 1. This is how I can write, no? Clear, no, ma? CV of mixture. So R gamma value also I have to write gamma of the mixture itself. Clear, no? So this is equals to N1 multiplied by CV1. CV1 how can I write? CV1. CV1 means CV of the first gas, gas number 1. R divided by gamma 1 minus 1 plus N2 multiplied by R divided by gamma 2 minus 1 divided by N1 plus N2. I can write like this, no? Are able to understand me? So therefore, R values if you cancel, okay? Therefore, what I am getting, so 1 by gamma of mixture minus 1 is equals to N1 divided by gamma 1 minus 1 plus N2 divided by gamma 2 minus 1 divided by N1 N2. This N1 N2 I can take to the numerator also. I can write N1 plus N2. Are you able to understand? So this is the total equation by which I can calculate gamma of the mixture of gases. Okay. And this equation also you can calculate for any number of gases. 2 gases, 3 gases, 4 gases. For any number of gases. Okay, ma? So N1 plus N2 divided by gamma of mixture minus 1 is equals to N1 by gamma 1 minus 1 plus N2 by gamma 2 minus 1. Okay. So all these calculations we have done for CV of mixture, no? Same calculations you can calculate for CP of the mixture also. Okay. Same format of the equation we will get. Similarly, CP of the mixture. This is equals to, so N1 CP1 plus N2 CP2 divided by N1 plus N2. Are you able to understand? So this is how we can calculate CP of the mixture. Are you able to understand, ma? So these, all the formulae, you must remember them carefully, ma. For mixture of 2 gases. If 2 gases are mixed, then how can I calculate their CP, CV and gamma values? This you have to by heart them very carefully. Clear, ma? So you should practice in the same format, ma. Whatever format we have used for deriving these equations, while practicing also you should follow the same pattern. Okay? So after practicing, then you should start by hearting this formula also. That's it. Right down. Fan off, sir. Okay, ma? So see what is the data which is given, ma? Data is, so gaseous mixture enclosed in a vessel consists of 1 mole of gas A. First gas how many moles, ma? 1 mole. And gas B. And how many moles of gas B is there? I don't know. So gamma 1 and gamma 2 values are given. Clear, no? Adiabatic constant of first gas, adiabatic constant of second gas, they are given. Temperature is also given. The gases A and B do not react with each other and are assumed to be ideal gases. So find the number of moles of gas B. So if gamma of mixture is also given. So what is the data which is given, ma? Data is gamma 1 is 5 by 3, gamma 2 7 by 5, gamma of mixture is how much, ma? 19 by 30. Clear, no? What he is asking us to find out number of moles of gas B. It means N2 value he is asking us to find out. N1 is already given as 1. That's all, no? Now where you find all these equations, all these parameters, where you can find in this relation, no? Okay, no? This relation avennii unnai kada. So N1 plus N2 divided by gamma mixture minus 1 is equals to N1 by gamma 1 minus 1 plus N2 by gamma 2 minus 1. So just substitute, and what we are supposed to calculate? We are supposed to calculate N2 value. That's all. Remaining all the values are present, no? Substitute. So if you substitute, I am writing the answer directly, ma. N2 value you should get to 2. Okay? What is the answer you should get, ma? N2 value is 2. That's it. I need not do, no, ma? I hope you can do it. All the values are given, no? Just substitute and see whether you get this answer or not. Okay? Okay, ma. So now we will study different processes which we do in thermodynamics, ma. How many processes are there? Isothermal, isobaric, isochoric, adiabatic, all these processes are there, no? So we'll study each of them in detail and we will try to understand actually what is happening in these processes. Clear, ma? So isobaric process means what, ma? Isobaric process is a process where pressure remains to be constant. That's all, no, ma? Bar is the unit of measuring pressure, no? Iso means same. Isobaric means same pressure. Pressure is a constant. So if I take ideal gas equation, PV is equals to nRT. What are the values which are constant and what are the values which are not a constant, ma? Pressure is a constant, no? Okay, ma? Number of moles is a constant. R value is also a constant. So what are the variables here? Volume and temperature, they are variables. That's all, no? So therefore, if pressure is a constant, volume is directly proportional to temperature. This is also called as Charles law. దీన్నే మనం చార్ల్స్ లా అని కూడా అంటాం కదా. So what is the process which is happening in isobaric process? Which law is applicable? Charles' law is applicable in isobaric process. Clear, no? So therefore, by using this relation, I can write V1 divided by T1 is equals to V2 divided by T2. Like this also I can write. Okay. So therefore, if I draw one graph, now these graphs you can call them as indicator diagrams. Indicator diagrams. Okay. So for example, if I write pressure, volume, clear, no? Then if I draw graph like this, then what do you understand by looking at this graph? Pressure is a constant, volume is increasing. See the direction of the graph. In this direction, no? It means I am moving from lower volume to higher volume, V1 to V2. Understood now? So therefore, this is called as isobaric expansion. What do you call this graph? This is called as isobaric expansion. Okay? ఈ డయాగ్రామ్స్ చదివినాం అక్కడ చదవలేదు చూడండి కొత్తది వచ్చింది కదా అలా ఓకే సిమిలర్లీ ఇఫ్ ఐ డ్రా వన్ మోర్ గ్రాఫ్ సేమ్ పీవీ గ్రాఫ్ అండ్ దిస్ ఈస్ ద గ్రాఫ్ నౌ వాట్ డూ యూ అండర్స్టాండ్ దిస్ ఈస్ ఐసోబారిక్ కంప్రెషన్ వాల్యూమ్ ఈస్ రెడ్యూసింగ్ నోమా సో వీఆర్ ట్రావెలింగ్ ఫ్రమ్ హయ్యర్ వాల్యూమ్ టు లోయర్ వాల్యూమ్ ఆపోజిట్ డైరెక్షన్ సో దేర్ ఫోర్ దిస్ ఈస్ కాల్డ్ యాజ్ ఐసోబారిక్ compression. Are you able to understand? Clear? So now if I study about first law of thermodynamics, see ma'am. So first law of thermodynamics. What is first law of thermodynamics in physics? So Q is equals to delta U plus delta W. That's all, no? Okay. So in isobaric process, definitely heat can be supplied, no? Can we supply heat energy or not? Definitely we can supply heat energy. Okay. Change in internal energy. Internal energy can increase, no? If I heat a gas at a constant pressure, yesterday only we studied, no? If I heat a gas at constant pressure, that heat supplied will do two things. Adu rendu panulu chestundi. One is, first of all, it will raise the temperature of the gas. If temperature rises, internal energy also rises. And remaining heat energy, it will be used for lifting the piston upwards. That is doing work on the piston. Okay. So therefore here, Q is not zero. Q is not zero means heat is definitely supplied. Heat is definitely supplied, or heat is taken out of the system also. That is, heat can be positive, heat can be negative, both can be present. Delta U is not zero. Delta U also it is not zero. Clear, no? Internal energy definitely will change. Okay. And work done also it is not zero. It means definitely piston moves. Piston either it moves upwards or it moves downwards. Both will happen. Okay. So in all the first law of thermodynamics, all the three parameters, no parameter is zero. Edi zero avatan ledhu ikkada. Is it clear? So this is one point which we have to study in the case of first law of thermodynamics. None of them is zero. Okay. Similarly, if I study specific heat of this gas, yes, here S can be written as Cp, no ma? S can be written as Cp. Why? I am heating the gas at constant pressure process. Cp. Cp is equals to Q divided by N delta T. This is the formula, no? What is the formula of specific heat? Q divided by N delta T. Q value, is it zero? No. Delta T, is it zero? No, because change in internal energy is not zero. No? If delta U is not zero, delta T also it is not zero. Temperature will definitely change. That is the meaning of it. Okay, ma? So Q is not zero, delta T also is not zero. So I say specific heat also it is not zero. That's all, no? So in isobaric process, specific heat of the gas cannot become zero. Similarly, work done in isobaric process. Next concept what we study? Work done in isobaric process. So all these processes you should have a very good idea. Until you don't understand these processes, you can never understand, you can never do the problems of thermodynamics. Okay? So work done. What are the formulae for work done, ma? So W is equals to P delta V is one formula. W is equals to integration of P dV, limits are applied from V1 to V2. This is one more formula. Out of these two, which one can I use? First one or second one? First one. Why? Pressure is a constant. So this formula I can use only when pressure is a constant. And this is isobaric process number. So this formula of work done, definitely I can use. This formula we cannot use. Are you able to understand? This is the formula in which condition? Pressure is a variable. When pressure is a variable, we use this condition. Because pressure is a constant, definitely we can use this relation to calculate work done. Or just you can write this relation, P multiplied by V2 minus V1 also. Is it clear? So this is the total concept which you should remember under isobaric process. Okay, ma? So what we have studied, first of all, we have drawn graphs. We have analyzed first law of thermodynamics. We have analyzed how specific heat will be and what is the equation for work done. Okay? In every process, we will do all these calculations. Come on. Okay, ma? So the next process which we are studying is isochoric process. What is meant by isochoric process, ma? Volume remains to be a constant. So let us again analyze the first law of this ideal gas equation, ma? So PV is equals to nRT. Okay? What are the terms which are constant and which are not constant? Volume is a constant. Number of moles of gas is a constant. R value is a constant. But pressure and temperature, they are not constant, but they are directly proportional to each other. What is this law? Gay-Lussac's law. This is called as Gay-Lussac's law. Clear, ma? Or you can call this as Heartless Law of Pressure also. Are you able to understand, ma? So therefore, I can write P1 by T1, it is equals to P2 divided by T2. So you can write like this also. Are you able to understand, ma? So therefore, and no need of drawing the graphs, already we have drawn many times. So we will directly study first law of thermodynamics. Okay? First law of thermodynamics. What is first law of thermodynamics? Q is equals to delta U plus delta W. Okay? So can you say what is the, first of all, heat is supplied or not, ma? Heat can be supplied, no? Isochoric process doesn't mean that you should not supply heat energy. You can supply heat energy, no problem. So Q is not zero. Change in internal energy, temperature can increase, no? So change in internal energy is not zero, or change in temperature also it is not zero. Work done? Work done is zero. Why work done is zero, ma? Work done is zero because volume is a constant, no? So piston cannot move upwards, piston cannot move downwards. So work cannot be done. Are you able to understand? So therefore, in first law of thermodynamics, what I can write? Q is equals to delta U plus 0. Okay, ma? So what do you understand? Q is equal to delta U plus 0 means what do you understand? Internal temperature, external temperature, okay. So the total heat energy which you supply, it is responsible for rising internal energy of the gas. Okay, ma? So మీరు supply మొత్తం energy కేవలం temperature పెరగటానికి మాత్రమే యూజ్ అవుతుంది. That is the meaning of it. Therefore what we write? Total energy supplied is utilized for what, ma? Is utilized for increasing internal energy of gas. Internal energy of gas. Are you able to understand? Clear, no, ma? Now let us study work done. How much is the work done, ma? Zero. Already we, first of all we have to study specific heat, no? Specific heat. Specific heat, S is equals to Q by N delta T. Okay, ma? Q by N delta T. Q value is it 0? Delta T is it 0? So S also cannot be 0. So I write S is not 0. Understood, no, ma? Now work done. Work done is how much? Work done is nothing but 0. Okay? Why work done is 0? Because piston cannot move upwards or piston cannot move downwards. So work done is 0. But in the previous condition, work done was not 0. In isobaric process, work done was P delta V. But here it is 0. అర్థమవుతున్నాయి కదా? Right. Now see. So the third process is isothermal process. Thermal indicates what? heat energy. It means temperature is a constant. Clear, Nama? So T is a constant. Now let us study ideal gas equation. PV is equal to nRT. Okay, ma? What are the terms which are constant? N is a constant, R is a constant, T is a constant. All of them, they are constants. Clear, no? But pressure into volume, product is a constant. That is the meaning of this one, no? So I can say the product of P into V is a constant. So therefore, pressure is inversely proportional to volume, or you can write volume is inversely proportional to pressure. That is the meaning of this one, no? It means if pressure increases, volume should decrease. Then only the product will be same. Okay? And this is what kind of law, ma? This is called Boyle's law. Okay? So, Boyle's law. Understood, no? So, how can I draw a graph of Boyle's law, ma? So, this is P, this is V. This is how I can draw the graph. Temperature is a constant. Already we studied, no? Why we have to draw a graph like this? Because as pressure increases, volume should decrease, and as volume increases, pressure should decrease. They are inversely proportional to each other. Now if I draw this arrow, then what do you understand? Then it becomes an indicator diagram. Are you able to understand, ma? If you draw the direction of arrow, it becomes an indicator diagram. Now what does this indicator diagram indicate? Volume is reducing, volume is increasing, pressure is decreasing. That is what we understand. Okay. Similarly, if I draw one more graph, so this is pressure and this is volume. So if I draw three types of graphs, then what do you understand? So this one is at a temperature of T1, at a temperature of T2, at a temperature of T3. What is the relation between T1, T2 and T3? T3 is greater than T2 is greater than T1. What is the reason? Already we have studied 1,000 times. Physics 500 times, chemistry 500 times. So no need of studied once again. So remember this one. Clear, Nama? Now we will study about first law of thermodynamics. First law of thermodynamics. What is first law of thermodynamics, ma? Q is equals to delta U plus delta W. Anything which is 0? Delta U is 0. Temperature is a constant, no, ma? Temperature remains a constant. It means change in temperature is 0. It means change in internal energy is also 0. Internal energy will not change in isothermal process. Okay? So therefore, Q is equals to delta W. What do you understand? Whatever heat energy you supply, total energy is used for doing work. That's it. Are you able to understand? So, your father has given 200 rupees for expenditure. You have spent total 200 rupees for eating pani puri. Now what is the amount you have? 0. Same concept here also. Are you able to understand? So whatever energy is given, total energy is doing for work only. So internal energy does not change. Is it clear? So that type of process is called as isothermal process. Understood, Nama? So therefore, now specific heat. What about specific heat, ma? Specific heat formula, S is equals to Q by N delta T. Delta T, 0. Anything by 0? Infinite. So specific heat in this condition is how much? It is infinite. Are you able to understand, ma? So in isothermal process, specific heat of a gas is infinite. Are you able to understand? Next what we study? Next we study about work done. Work done in the case of isothermal process. Okay, ma? So work done in isothermal process can be written as 2.303 nRT log V2 divided by V1. This is the formula. Okay, ma? Log to the base 10. Or same formula you can write nRT natural logarithm of V2 divided by V1. Same formula you can write 2.303 nRT log to the base 1 P1 divided by P2. Same formula you can write 2.303 nRT natural logarithm of P1 divided by P2. So these are the different formulae which we can use in the case of work done in the case of isothermal process. Understood, Nama? These formulae we have written in thermodynamics in chemistry also. Ma. Clear? Same formula. So see, ma, if you are writing natural logarithm, then you just write nRT log V2 by V1. Okay? See, ma, here this is an isothermal process where pressure is inversely proportional to volume, no? So if you write V2 by V1, same V2 by V1 can be written as P1 by P2 also. Okay? If you want to represent in terms of pressure, you have to write P1 by P2. Derivation is there, ma. We are not going for derivation. Because derivation, I don't think he will ask in NEET exam. NEET exam lo derivation adagadu kada, so avasam ledhu manaku. Just to remember the formula. Clear? So if it is written to the base of log 10, then you will get to 2.303. Okay, ma? Log to the base E, which is called natural logarithm. Then you have to write just nRT. That's it. These are the formulae which we have in isothermal process. Understood, no? Now, let us see the conditions of doing isothermal process. Okay, ma? Conditions of isothermal process. Okay. So what is meant by isothermal process, ma? Isothermal process means temperature should be constant. So in which condition temperature can be constant? See, for example, so listen to this one very, very carefully, ma. So this is a piston and a gas is present inside this piston. So by applying some force, I am making this piston go downwards. I am compressing the volume of this gas. Okay, ma? So if I am compressing the volume of this gas, it means I am doing some work on the gas, no, ma? That work should be converted into some another form by law of conservation of energy. Are you able to understand? So the work which you do, it will increase the internal energy of the gas. Meeru chesina work deniga marutundi, gas yokka internal energy ga marutundi. Automatically what happens to the temperature? Temperature also will increase. But temperature should remain constant, no, ma? What is isothermal process? Temperature should remain constant. How it is possible? You are doing work, automatically temperature increases, but I don't want the temperature to increase. We have to compress this piston very, very, very slowly. Infinitesimally slowly. That is the actual word which we should use. It means we have to press the piston so slow that as soon as there is a change in temperature, heat energy goes out of the walls of the container and temperature again remains constant. Okay? So first condition is that walls should be diathermic walls. What is meant by diathermic walls, ma? They can transfer heat energy out of the system and into the system also. Heat energy ni rendu vaipula pampinchagalugutayi. They are called as diathermic walls. Second one is process should be very slow. Process should be very slow. So these are the two conditions in which we can perform isothermal process. Are you able to understand? That's it. Okay, ma? So in same isothermal process, we have to study once again about, okay, ma? We have to study about the slope of PV graph, which is also important, which can be asked in the examination. Okay, ma? So slope of PV graph. Okay, ma? So this is pressure and this is volume. This is the shape of the graph which I draw, no, ma? So how to calculate the slope of this graph? You take any one point, ma, and by touching that point, you draw a tangent. Okay? If you split this tangent into two components, this is a change in volume, no? And what is this vertical line? This is change in pressure. Okay? Then if you take the ratio of delta P by delta V, that is called as the slope of this graph, tan theta of a graph. Okay? So if I take this angle to be theta, then delta P divided by delta V, that is called as slope of the graph. Okay? How can we derive this one? Let us see. Sima. See, in isothermal process, PV is a constant, no? Isothermal process means temperature is a constant. So product of P into V also is a constant. Now if I differentiate this one, I can write it as P dV plus V dP, this is equal to 0. Because the differentiation of a constant is 0. Okay? Differentiation of AB, this is how we do, no? A multiplied by differentiation of B. V multiplied by differentiation of A. And differentiation of a constant is 0. So therefore I can write P dV is equals to minus V dP. Clear, no, ma? So dP divided by dV is equals to minus P by V. This is called as slope of the graph. Slope of which graph? Isothermal graph. or isothermal process. Okay, ma? This is the formula to calculate slope of a graph. Slope of isothermal graph. Are you able to understand, ma? dP by dV is equals to minus P by V. So just you take the negative ratio of pressure and volume, that will give the slope of the graph. Are you able to understand? So these are all the points which we should study in the case of isothermal process. Clear, ma? Right. Okay, ma? Now see. So the fourth process which we are studying is adiabatic process, ma. What is meant by adiabatic process? Adiabatic process means in this process, Q value is 0. Q is not positive, Q is not negative, Q is 0. What is meant by Q is 0? Heat is not taken inside the system, or heat is not given by the system also. Heat తీసుకోదు, heat ఎవరికి ఇవ్వదు అన్నమాట. Clear? So therefore, if I study first law of thermodynamics, then Q is equals to delta U plus delta W, and this statement we have to understand very, very carefully. So see. So 0 is equals to delta U plus delta W. This is how I have to write. So therefore, delta U is how much? Delta U is negative of delta W. Okay, ma? Or also I can write delta W is equals to negative of delta U. Clear, no? Now when you study these two statements, what do you understand? ఈ రెండు స్టేట్మెంట్స్ను చూస్తే మీకేం అర్థమవుతుందో చెప్పండి. ఎక్స్ప్లెయిన్ దట్ వన్. వాట్ ఈస్ ద మీనింగ్ ఆఫ్ దిస్? పెరిగితేనా తగ్గితేనా? టెంపరేచర్ ఇఫ్ ఇట్ ఇంక్రీజెస్, వర్క్ డన్ విల్ బి నెగిటివ్. ఓకే. సో ఫర్ ఎగ్జాంపుల్ ఇఫ్ ఐ టేక్ దిస్ సిస్టమ్, క్లియర్? సో దిస్ ఈజ్ అ పిస్టన్. Okay, now try to explain this statement, ma. Perutundi. Clear, na ma? See, ma, if I push the piston downwards, okay, ma, then piston starts coming downwards, no? Piston moves downwards. If piston moves downwards, gas is compressed or gas is expanded? Compressed. So work done by the gas is positive or negative? Work done by the gas is negative. Clear, na ma? And what is delta U? If work done is negative, then delta U should be positive because they are separated by minus sign, no? It means internal energy of the gas increases. That is the meaning of this one, no? Are you able to understand? And that is understandable, no? If anybody compresses the piston, that work done will be converted into internal energy of the gas. So temperature will rise, but heat energy will not escape the system. What kind of walls they will have? So first of all we will write conditions of performing adiabatic process. Okay, ma? Conditions of performing adiabatic process. First condition is what kind of walls they should have? Adiabatic walls they should have. What is meant by adiabatic walls, ma? They doesn't transfer heat energy. Heat energy will not leave the system, heat energy will not enter the system also. So adiabatic walls. So, but can you give any example of perfect adiabatic wall, ma? Perfect adiabatic wall. థర్మోఫ్లాస్క్లో మీరు టీ వేసి పెడితే 4 గంటలు 5 గంటలు చల్లగా అవ్వదు, కానీ 10 రోజులు పెడితే చల్లగా అవుతుంది కదా. It means it is not a perfect adiabatic wall. Thermoflask is not a perfect adiabatic wall. Perfect adiabatic wall. ఫ్లాస్క్లో వేస్తేనే చల్లబడుతుంది, గ్లాస్లో వేస్తే చల్లబడతారు ఇంకా. పర్ఫెక్ట్ అడియాబాటిక్ వాల్. దెర్ ఈస్ నో పర్ఫెక్ట్ అడియాబాటిక్ వాల్. క్లియర్ నమ్మా? సో యాజ్ దెర్ ఈస్ నో పర్ఫెక్ట్ అడియాబాటిక్ వాల్, okay ma, perfect adiabatic wall is not there. So therefore what we do, so we perform the process very fast such that heat energy does not find time, to escape into the system. Okay, ma? Or out of the system also. or out of system. Are you able to understand what is happening, ma? Because there is no 100% adiabatic wall, perfect adiabatic wall, what we do is, we perform the system suddenly. Within 0.1 seconds, we will do the process. So even temperature increases, suddenly heat energy cannot flow into the surroundings. No? It takes some time. అంతే కదమ్మా. సో ఇప్పుడు వాటర్ స్టవ్ మీద పెడుతూనే ఒకేసారి పొంగడం స్టార్ట్ అవుతాయి, అవి వేపర్గా మారవు కదా. హీట్ టేక్స్ సమ్ టైమ్ టు ట్రాన్స్ఫర్. ఓకే, సో వీ డూ ద ప్రాసెస్ వెరీ ఫాస్ట్ సో దట్ heat energy doesn't go into the surroundings, or it is not taken from the surroundings also. Clear? In isothermal process, we do the process very slow. But here we are doing the process very fast. That is called as adiabatic process. Are you able to understand, ma? So actually what we were discussing, now see, ma. Now let us come to the old concept. So delta W is equals to negative of delta U means what? If you do positive, we are discussing about this one, no? So if work done is negative, then that total work done on the gas, which is positive. This is work done by the gas, no ma? Delta W means what? Work done by the gas. If it is negative, then work done on the gas is positive. Clear? So if positive work is done, that positive work converts into internal energy. Total internal energy. Is it clear? But temperature increases, but heat energy doesn't flow into the system, or it doesn't go out of the system. Okay. Similarly, if I want to study about this equation, let us see this one also. Okay, ma? Now what is this one? So consider this is a piston, gas is present inside this cylinder. Okay, ma? And gas is pushing the piston upwards. Gas is pushing the piston upwards. It means delta W positive. Work done by the gas is positive. Then what happens automatically? Internal energy should decrease. That is the meaning of this one. No? Negative of delta W means what? Internal energy should decrease. How internal energy is decreasing? No? Because gas is doing some work. Okay? Who is moving the piston upwards? Gas. So it is spending some energy, no? Because it is spending some energy, its energy reduces. Are you able to understand? జయంతి తల మీద 10 వద్దులేండి, ఒక వాటర్ క్యాన్ పెట్టి కిందికి పోయి క్యాన్ తేయండి అని చెప్పినాం అనమాట. జయంతిని పోయేటప్పుడు బాగానే ఉంటుంది, వచ్చిన తర్వాత ఏముంటుంది, అటు నుంచి అట్టే అంబులెన్స్ మాట్లాడుకొని మనం తీసుకెళ్ళాలన్నమాట. ఎందుకు అట్లా? వర్క్ చేసింది కదా, షీ హ్యాస్ స్పెంట్ సమ్ energy. Same concept here also. Who is pushing the piston upwards? Gas. So what happens to the internal energy of the gas? Reduces. Are you able to understand? So this is how we can explain these two equations. Clear, Nama? Make a note up to here. Okay, ma. So these are the relations which we should remember in adiabatic process, ma. Clear? So relation between PV, relation between T and V, relation between T and P. Direct questions will be asked on these relations, ma. Okay? So PV power gamma is a constant, first relation between pressure and volume. Okay? What is gamma? Gamma is called adiabatic constant number. The ratio of Cp divided by Cv is called as gamma. So PV power gamma is a constant. For two different gases, or for same gases at two different conditions, how can I compare them? I can compare them like this. Okay, ma? So P1 V1 power gamma is equals to P2 V2 power gamma. I can write like this. Are you able to understand, ma? So this is initial pressure, this is final pressure. Initial volume, final volume. So like this questions can be given. Okay. Similarly, relation between temperature and volume is TV power gamma minus 1. So again, in two different conditions, how can I compare? T1 V1 power gamma minus 1 is equals to T2 V2 power gamma minus 1. This is the equation. Understood, no? One more relation between temperature and pressure is P power 1 minus gamma is a constant. So we have derivations for all of them. No derivation is required, just you by heart the formula. Clear? So therefore, T1 P1 power 1 minus gamma is equals to T2 P2 power 1 minus gamma. These are the relations. Okay? And these are the equations for work done in the case of adiabatic process. Okay? So what is the work done in adiabatic process? In terms of pressure and volume, P1 V1 minus P2 V2 divided by gamma minus 1. In terms of NR and T, NR into T1 minus T2 divided by gamma minus 1. Okay. Now we study about slope in the case of adiabatic process. Specific heat. Okay, ma? So what is the equation of specific heat, ma? Q divided by N delta T. This is the equation, no? Okay. Now what about Q? Q is 0. In adiabatic process, Q will be 0, no? Clear, no? N value, N is not 0. Change in temperature? Change in temperature is not 0. Temperature can change. Only heat energy cannot enter into the system. Heat energy cannot go out of the system. That's it. Okay? So 0 divided by N delta T. 0 by anything? 0. So specific heat of adiabatic process is how much, ma? Specific heat of adiabatic process is 0. Is it clear? That's it. Okay? Okay, ma? Now see. So next we are trying to derive an equation for slope in the case of adiabatic process. Okay, ma? So P V power gamma is a constant. This is one relation between pressure and volume, no, ma? P V power gamma is a constant. Now if I differentiate this relation, so P differentiation of V power gamma. Differentiation of V power gamma I can write like this, no, ma? So differentiation of x power n is how much? N into x power n minus 1. That's all, no? So therefore gamma into V power gamma minus 1. I have differentiated only gamma. V I have not differentiated, no? So again I will write dV. Understood, no? Then V power gamma, now I will take a constant, and differentiation of dP is dP only. So total should be how much? Total should be equal to 0. Understood, no? Is it clear, ma? If it is not clear, you ask me once again. Okay? Now see. Now what I want to calculate? I want to calculate dP by dV. That is the slope of any graph, no? So therefore what I will do? So V power gamma dP is equals to negative of P gamma V power gamma minus 1 dV. Okay? Now if you take dP by dV on one side, dP divided by dV is equals to minus P gamma V power gamma minus 1 divided by V power gamma. Okay? Is it correct, ma? Correct only, no? P gamma V power gamma minus 1 by V power gamma. So therefore dP divided by dV is equal to how much, ma? So minus gamma P by V. This is the relation. Okay, ma? So this is the slope of which process? Slope of adiabatic process. Okay, ma? So slope of adiabatic process. What is the slope of isothermal process, ma? dP by dV of isothermal process is how much? Minus P by V. But what is the slope of adiabatic process? Gamma P by V. Minus gamma P by V. Gamma value greater than 1 or less than 1? Gamma is always greater than 1. Because gamma is the ratio of Cp by Cv. Cp is always greater than Cv, no? So gamma is always greater than 1. Okay, ma? If gamma is always greater than 1, it means slope of adiabatic process is always greater than slope of isothermal process. It is negative slope. But still magnitude wise it will be greater. Okay, ma? Therefore what we say, slope of adiabatic process is always greater than slope of isothermal process. So always the slope of adiabatic process will be greater when compared to isothermal process. For example, if any two graphs are given, okay, ma? For example, he will give graphs like this. Okay? So this is pressure and this is volume. This is one graph and this is another graph. Okay? So he will ask you to find out which one is isothermal and which one is adiabatic. ఈ రెండిట్లో adiabatic ఏది, isothermal ఏది? This is isothermal, this is adiabatic. Are you able to understand why? Slope of this graph is greater, no? ఇది ఎక్కువ స్టీప్గా ఉంది కదా, ఇది ఫ్లాట్గా ఉంది ఫస్ట్ గ్రాఫ్. Whose slope is greater? Slope of this graph is greater. So this is adiabatic. Slope of this one is not so steeper. So therefore that is isothermal. Are you able to understand? So wherever you find a greater slope, it always indicates that it is the slope of adiabatic process. Are you able to understand? So for example, if I draw 4 graphs, okay? So this is one graph, this is one graph, this is one graph, and this is one graph. 1, 2, 3, 4. Okay? Now can you say which is isothermal, which is adiabatic, which is isochoric, and which is isobaric? Fourth one is adiabatic. Nee talakai murder chestanu. First of all, this is which graph? First graph. This is isobaric process. Why this is isobaric, ma? Pressure is a constant. Pressure constant ga undi kada. This graph was directly given in the previous examinations, ma. Okay? What about fourth graph? Isochoric graph. Volume is a constant, no? This is which kind of graph? Isochoric graph. Now out of these two, which one is adiabatic, which one is isothermal? Third one is adiabatic. This is adiabatic. Why? Slope is greater, no? This is isothermal. Why? Slope is lesser. Okay, ma? See, ma, you can compare isothermal and adiabatic only when you look at their graphs. Very optional, I think. Okay? Right on. Okay, ma? So now we are trying to understand the isothermal and adiabatic processes, ma, by taking two conditions. First condition is equal expansion, and the second condition is equal compression. See, ma, listen very carefully. See here, there are two PV graphs. No? This is one PV graph and this is another PV graph. Two PV graphs are present in same graph. So out of them, which one is isothermal and which one is adiabatic? Ma? Adiabatic is isothermal. So this one is isothermal. Clear, no? And the second one is adiabatic process. Okay. So therefore, final volume of which one is greater? Final volume is same for both of them, no? So first condition which I can write is final volume is same for both of them, for both processes. Understood, Nama? It means we are expanding both the gases. This is expansion only, Nama. Initial volume was how much? Initial volume was V1, final volume was V2. Definitely V2 is greater than V1, Nama. Final volume is greater than initial volume. It means this is the concept of expansion, and we are expanding the gas in two processes. First I am expanding by using isothermal process, then I am expanding by using adiabatic process. Both processes we are using. Now can you say pressures? How can you compare pressures, ma? Pressure of isothermal, pressure of adiabatic. Now can you say which one is greater here? Pressure of isothermal is greater or pressure of adiabatic process is greater? Finally. So compare the pressures. This is the pressure of adiabatic process. This is the pressure of isothermal process. Understood, Nama? So therefore, which pressure is greater? Pressure of isothermal process is greater than pressure of adiabatic process. Is it clear? Now I want the reason of this one. This is what I am trying to explain you. Can you say when I expand this gas in two different processes, can you say why the final pressure of isothermal process is greater than pressure of adiabatic process? In both of them it is proportional to 1 by V only, no? Okay, ma? Volume is same. Final volume of both of them is same. Initial volume is also same. Are you able to understand? Both of them, they are starting from this state, no, ma? Finally they have reached to this state. Final volumes are same. Expansion in expanding. For example, let us consider initially 1 liter of gas was there. I have expanded the gas to 2 liters of volume. In how many processes? Both processes, both isothermal as well as adiabatic. Volumes are same. Initial volume is also same. Final volume also same. But I see that pressure of isothermal process is greater than pressure of adiabatic process. Why? Why is it like this? If slow or fast? Okay, why I got slope like that? దేంట్లో టెంపరేచర్ రైజ్ అవుతుంది. ఇంకోసారి థింక్ వన్స్ అగైన్. Sima, I will explain you very clearly. Sima. First of all, what is isothermal process? Isothermal process means this process will have diathermic walls, no ma? Diathermic walls it will have. What is meant by diathermic walls? Heat can go out of the system, heat can come into the system also. That is the walls of isothermal process. So if I start expanding the gas in isothermal process, so if gas expands, temperature should fall down, no? If gas expands, what should happen to the temperature? Temperature automatically falls down. So if temperature falls down, heat energy enters from surroundings into the system. So the temperature always remains same. This is isothermal process, no? When you start expanding the gas, what happens to temperature? Temperature falls down. Once temperature falls down, heat energy enters from where to where? From surroundings into the system. That is what happens, no? So that is why the temperature of isothermal process remains same. Now if you come to adiabatic process. Adiabatic process, if you expand gas, here also temperature reduces. No? If you expand any gas, temperature reduces. Okay, ma? But heat energy, can it enter into the system? Heat energy cannot enter into the system. Why? What type of walls it has? It has adiabatic walls. What type of walls untai diniki? It has adiabatic walls. So here temperature reduces. Are you able to understand? But here temperature does not reduce. If temperature reduces, it means speed of the molecules has reduced, no? If speed reduces, automatically pressure also reduces. That is the reason why it has lesser pressure when compared to adiabatic process. Isothermal process. అర్థమవుతుందా ఏం జరుగుతుందో? క్లియర్ మా? సో అండర్స్టాండింగ్ ఆఫ్ కాన్సెప్ట్ ఈజ్ వెరీ వెరీ ఇంపార్టెంట్ మా. క్లియర్? మనం ఫార్ములాలు బట్టి కొట్టేసి రాద్దామంటే కుదరదు అట్లా. కాన్సెప్ట్ క్లారిటీ ఉంటే కాన్సెప్ట్ పైన వాడి కోసం అడుగుతాడు. ఇస్ ఇట్ క్లియర్? సో here in isothermal process, temperature does not fall down. Enduku? Because temperature is, heat energy is entering into the system. But here temperature falls down and heat energy cannot enter into the system. Are you able to understand? So here temperature is same, but here temperature falls down. Once temperature falls down, speed of the molecules reduces. If speed reduces, definitely the pressure exerted by the molecules also will be lesser. That is why you will have a lesser pressure. Are you able to understand, ma? That is the reason of this one. Okay. Now try to explain this one, ma. Try to explain this one. Now this is compression. No? Why it is compression? Okay, ma. Because initial volume was V1, final volume was V2. And which volume is greater? V1 is greater than V2. So definitely this is an example of compression of a gas. Are you able to understand, ma? Now both of them started from same volume, both of them ended at same volume. Final volumes are same. That is why it is called equal compression. Okay? So therefore what I say that final volumes are same. Final volumes are same. Okay, ma? But can you say which pressure is greater, ma? Which pressure is greater? So first of all, out of these two graphs, which is isothermal, which is adiabatic? First one is, this one is, this one, isothermal. Slope is lesser, no? Which graph is having greater slope? This graph is having greater slope. This is an adiabatic process. Okay? So pressure of which process is greater? Pressure of adiabatic process is greater than pressure of isothermal process. Clear, no? So therefore definitely I can write pressure of adiabatic is greater than pressure of isothermal. But previously, pressure of isothermal was greater than pressure of adiabatic. But here you got a reverse process. Okay. Now how can you explain this one? How can you explain? When you are compressing the gas, this is compression only, no? When you are compressing the gas, pressure of adiabatic, final pressure, is greater than pressure of isothermal process. How can you explain this one? If you understand these concepts, ma, you will clearly understand what is meant by isothermal, what is meant by adiabatic. Chappan. Right. That is the reason. Clear, nama? See, ma, when you take a piston, gas of piston, and you start pushing it downwards. Okay? If you start pushing it downwards, if it is an isothermal process, which process, ma? If it is an isothermal process, as you start pushing the piston downwards, you are doing some work on the piston paina work chestunnaru kada. So that work converts into internal energy. So temperature of gas, what happens? Temperature of gas will increase. But as the temperature increases, what kind of walls it has? Diathermic walls. So heat energy flows out of the system. Clear, nama? Heat energy flows out of the system and temperature remains constant. But the same process if you do with adiabatic walls, then heat energy cannot flow out of the system. So temperature increases. Temperature increases. When temperature increases, energy of molecules increases. If energy increases, pressure also increases. That is the reason. Is it clear, ma? So this much information you can get from these two processes. Clear? So write down. So here what I can write. Did you make a note of the graphs, ma? So here what I can write. First of all, make a note of this. Okay, ma? So what we write here, we write in expansion, heat energy enters the isothermal process. Okay, ma? So final pressure will be greater. Simply I can write the reason like this. Clear, ma? In compression, what happens? In compression, heat energy leaves the system. Okay, ma? So pressure decreases. Understood, no? Whereas in adiabatic process, heat doesn't enter, heat doesn't leave also. So no problem. These are the reasons briefly which I can write down. Clear, no? That's it. Sima. So if I compare the temperatures, this is expansion, no? Expansion. Expansion means in adiabatic process, temperature reduces. That's all, no? But in isothermal process, temperature does not reduce. So therefore, final temperature in isothermal process is greater than final temperature in adiabatic process. Definitely I can write a relation like this, no? Clear, no? Similarly, compression. In compression, what happens? In compression, in adiabatic process, temperature increases. But in isothermal process, temperature remains same. So temperature of adiabatic is greater than temperature of isothermal. Okay, ma? Next, what about work done? Work done in which process is greater? In expansion. Huh? Work done in isothermal is greater. How can you say? Area under the graph. Work done under PV graph is nothing but area under PV graph, no? So which area is greater? Area under isothermal is greater when compared to adiabatic. Therefore, what I say, work done in the case of isothermal is greater than work done in the case of adiabatic. Okay? Because just area of the graph. Area of which graph? Only PV graph. Area of PV graph gives work done. What about here, ma? Which area is greater? Area under adiabatic is greater when compared to isothermal. So therefore, work done under adiabatic process is greater than work done under isothermal process. Is it clear? So these many informations I can get from these concepts of equal expansion and equal compression. Okay. So let us see the question. So in a cylinder, 2 moles of an ideal monoatomic gas, initially at 1 into 10 power 6 Pascal and 300 Kelvin temperature, expands until its volume becomes double. Okay. And we are supposed to calculate work done for this expansion in 3 different processes. What is the work done in isothermal, adiabatic and isobaric? Okay, ma? So do you remember what is the formula for work done in the case of isothermal process? Work done. Chapandi. See the books, ma. See what is the equation for work done in the case of isothermal process? Work done is equals to 2.303 nRT log V2 divided by V1. This is the equation. Okay, ma? And here values are given in terms of volume only, no, ma? So I will write V2 by V1. If values are given in terms of pressure, I will write P1 by P2. Okay. Now substitute all the values. So this is the work done in which process? Isothermal process. Okay. So therefore it is 2.303. Number of moles are how many? 2. R value 8.31. Temperature 300 multiplied by log of volume is becoming double number. So I will write 2V divided by V. Can I write like this? Initial volume is V, final volume is 2V. So therefore if you do this total calculation, that will be the work done in the case of isothermal process. And the answer which you should get is 3452 joules. 3452 joules. So this is the work done in the case of isothermal process. Are you able to understand? Similarly, now we will study what is the work done under adiabatic process. Okay, ma? So what is the equation of work done in the case of adiabatic process, ma? NR T1 minus T2 divided by gamma minus 1. This is the equation. Understood, no? So N value I know, R value I know, gamma value I know because it is a monoatomic gas. But final temperature I don't know, no, ma? Clear? See, in this equation, n we know. N is how much? 2. R also, R value also we know. R value is how much? 8.31. Okay. Initial temperature also I know, which is equal to 300 Kelvin. And gamma value also we know. What is the gamma value of a monoatomic gas? It is gamma value 5 by 3 I think. Gamma value 5 by 3. 5 by 3 only, no? For monoatomic gas, gamma value 5 by 3 only, no? 5 by 3. Clear, no? So, how can I calculate a T2 value? T2 value is not given, no? When I expand this one to double volume, what is the final temperature? That I don't know. Can you say how can I do? Anybody? So there is a relation Tv power gamma minus 1, it is a constant. These are the equations which we have to write in the case of adiabatic process. No? Pv power gamma, Tv power gamma minus 1, Pt power 1 minus gamma, all of them they are constants. So this is one relation. Tv power gamma minus 1 is a constant, and these equations are suitable for adiabatic process. Clear, no? So therefore what I can write, T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. This is how I can write, no? Okay. So what is the initial temperature? Initial temperature is 300. Initial volume V power gamma 5 by 3 minus 1. This is equals to final temperature, I don't know. Final volume is 2V. 2V power gamma 5 by 3 minus 1. Okay, ma? V and V get cancelled. So just to calculate T2 value from this one, that will be my final temperature in the case of adiabatic process. Okay, ma? And these calculations I am not explaining, ma. I hope you can do them. Clear? So therefore, final temperature which he gave is 189 Kelvin. 189 Kelvin. Okay. Now substitute in this equation. So therefore, what is the equation for work done, ma? W is equals to number of moles are 2. R value is 8.31. Initial temperature is 300. Final temperature is 189 divided by gamma value is 5 by 3 minus 1. Okay. If you do this total calculation, then the answer which I will get is, so it is 2764 joules. So 2764 joules. That is how we calculate work done in the case of adiabatic process. Okay, ma? Completed? Now let us see how we can calculate work done in the case of isobaric process. Okay. So what is the equation of work done in the case of isobaric process, ma? So isobaric process. Isobaric means pressure is a constant, you know. Pressure is a constant indicates work done can be written as P into delta V. Okay. P into V2 minus V1. This is the equation, no, ma? V2 minus V1. Okay. But volumes are they given? Volumes are they given, ma? Initial volume do we know? Final volume? We don't know. Then how can I calculate initial volume or final volume? See, ma, in the previous condition, in isothermal in process, they were getting cancelled. V2 by V1. So 2V by V, V was getting cancelled. But here I have to multiply V here. It means I need to calculate V. Initial volume I don't know. How can I calculate? V1 by T1. But this is which process? Okay, isobaric process, no, ma? V1 by T1 is equals to V2 by T2. Correct only, no? That method I can use. Okay. Any other method? Isobaric process, no? So, final temperature, I don't know, no, already. But this is the final temperature in which process? Adiabatic process. Final temperature, I don't know. Ideal gas equation we can use, no? What is ideal gas equation? PV is equals to nRT. Are you able to understand, ma? So therefore, initial volume, how can I calculate? nRT divided by P. I can calculate by this method. Number of moles, 2. R value, 8.31. Initial temperature, 300. Initial pressure, 10 power 6 Pascal. Okay. If you calculate all of them, I will get initial volume. Okay. And let us see what is the initial volume. Initial volume is how much? 4.98 into 10 power minus 3. 4.98 into 10 power minus 3 meter cube. This is the initial volume. Then what is the final volume? Final volume is just double of this one, no? Final volume double in the Nadagada. Okay. So therefore V2 is 2 times of V1. So 2 into 4.98 into 10 power minus 3. Clear, nama? So take all these values, substitute in work done. So work done of isobaric process is, pressure is how much? 10 power 6 multiplied by change in volume. Change in volume is how much, ma? So 2 into 4.98 into 10 power minus 3 minus 4.98 into 10 power minus 3. Okay. So if you do this total calculation, I will get, okay, so 4980 joules. So that is my work done in the case of isobaric process. Is it clear, ma? Just a direct substitution of formulae, and wherever we don't know the values, we are using different method. This is the method which we have used in adiabatic process, and just we have used ideal gas equation for isobaric process. Clear? Okay, ma? So let us see this question, ma. So 1 mole of perfect gas at 10 power 5 Newton per meter square. What is this one? This is initial pressure, no, ma? And this is initial temperature. So it expands isothermally until its volume is doubled. Okay, ma? It means if I consider this is the initial volume V, then it is expanding until its volume will become 2V. That's all, no? And in the first process, it is expanding isothermal. Expanding means volume is increasing, no, ma? So we are moving from V to 2V. So definitely this is the process, isothermal process. And then the gas is performed, again adiabatic process is performed, again its volume is becoming doubled. Okay. It means from here onwards, what is the next process we are performing? Adiabatic process. See, already we studied that slope of adiabatic process will be always greater than slope of isothermal process. This already we have studied, no? So that is why we have drawn graph like this. If this is isothermal, this one is definitely adiabatic, because slope of second graph is greater than slope of first graph. Okay. So volume is again doubled, means here how much will be the volume? 4V. So V double 2V, double of 2V is again 4V. So this is the process which is done. So therefore, now let us see what is the initial pressure. So initial pressure P1 is 10 power 5 Newton per meter square, or you can say Pascal. And initial temperature is 300 Kelvin. Okay, ma? Then what we are supposed to find out? Then find final pressure and final temperature of the gas. That is the question. Okay, ma? So first of all, we will study in isothermal process. Isothermal process. Okay. So what is meant by isothermal process? Temperature is a constant. This is called as isothermal process, no? Clear? So if temperature is a constant, a relation exists between which terms? Pressure and volume. So therefore I can write P1 V1 is equals to P2 V2. This is the relation of relation in terms of pressure and volume for isothermal process. PV is a constant. Do you remember all of them? In ideal gas equation, PV is equal to nRT. nRT is a constant because N is a constant, R is a constant, T is also a constant. So PV is also a constant. So P1 V1 is equals to P2 V2. So what is the initial pressure? 10 power 5. Okay. Initial volume V. Final pressure, I don't know. Final volume is 2V. Clear, no? So V and V get cancelled. So P2 value is how much mass? It is a 10 power 5 divided by 2, which is 0.5 into 10 power 5 Newton per meter square. So this is the pressure after which process? After isothermal process. Understood, Nama? We are supposed to study the final pressures and temperatures. First of all, I should know what is the final pressure after isothermal process, no? So this is the final pressure after performing isothermal process. Then what is the final temperature, ma? Final temperature? Same, because this is isothermal process, no? So here what is the temperature? Here temperature is 300 Kelvin. So definitely here also temperature will be T2, which is equal to T1, which is again equal to 300 Kelvin itself. So this is again equal to 300 Kelvin. Okay. So therefore, final pressure and final temperature after performing isothermal process we have calculated. Clear? Now we will go for which process? Adiabatic process. Okay, ma? So in adiabatic process, what is the relation between pressure and volume? PV power gamma is a constant. What kind of gas, ma? Monoatomic or diatomic?
Perfect gas.
Perfect gas is okay. What kind of gas is this? It is not given, no? Let us see the question. Gamma value is already given in the question itself, ma? So gamma is equal to 1.4. That is what he gave. Okay. Now adiabatic process. So relation between pressure and volume in adiabatic process. PV power gamma is a constant. This is the relation number. So therefore, for two different conditions, how can I write? I can write P1 V1 power gamma is equals to P2 V2 power gamma. This is how I can write. This is how I can write. So what is the initial pressure? Initial pressure is 10 power 5. Initial volume is V power gamma. Final pressure, I don't know. Final volume 2V power gamma. Initial volume is double, no? Very good. So, yes ma'am. So here volume was V, this was 2V, this was 4V, no? So here initial volume is 2V, here initial volume is 4V. Are you able to understand? So therefore this is 2V and this one is 4V. Clear number? So now V power gamma, they will get cancelled. So V get cancelled. So therefore P2, how can I write? P2 is equals to 10 power 5 multiplied by 2 by 4 power gamma. So 10 power 5 multiplied by 1 by 2 power gamma value is how much? 1.4. Okay. And if you do this calculation, I will get final pressure after performing which process? After performing adiabatic process. Clear number? And the answer is 1.2 into 10 power 4. 1.2 into 10 power 4 Newton per meter square. Okay. Are you able to understand? This is the final pressure after performing this process, after performing adiabatic process. Clear? Similarly, final temperature also I need to find out number. Final temperature, which relation? So TV power gamma minus 1, it is a constant. Clear? We can do. T, what is the relation? T power 1 minus gamma is a constant. That relation also you can use. Okay. So therefore here I will use T1 V1 power gamma minus 1 is equals to T2 V2 power gamma minus 1. That is the relation. Are you able to understand? Now substitute the values. Okay, ma. Initial temperature 300. Initial volume 2V power gamma minus 1. So final temperature, I don't know. Final volume 4V power gamma minus 1. So again V and V get cancelled here. So therefore T2 is equal to 300 multiplied by 2 by 4 power gamma minus 1. So therefore T2 value is how much? It is 300 multiplied by 1 by 2 power 1.4 minus 1. Okay. So if you do this calculation, we will get final temperature. And final temperature is 227.35 Kelvin. 227.35 Kelvin. So this is how we can calculate the final pressures and final temperatures. Is it clear, ma, how we have calculated? Just we have used the equations of isothermal process and we have used the equations of adiabatic process. That's it. Okay. Okay. Student, now let's see this problem. So this is the given question, ma. So this is a cylindrical cylinder container in which there is a piston which is present exactly at the middle, ma. So this piston is a movable piston. And all the walls, they are non-conducting. It means all the walls are adiabatic walls. Are you able to understand? So if piston is a movable piston, definitely one thing which I can say is pressure on both sides will be same, no? That's all, ma. Because if on one side if pressure is greater pressure will push the piston forward. But if piston is in rest position, it means that pressures are same on both sides initially. And in the problem also he gave that pressure, volume, temperature, they are same. Number of moles of gas also it is same. But one is a diatomic gas and second gas is a monatomic gas. For example, this one you can consider helium, this one you can consider oxygen. This is oxygen, this is helium. Diatomic gas, monatomic gas. Now what I am doing is, I am supplying electric current to this heater. So heater starts supplying heat energy. Okay, ma? So when heater starts giving heat energy, what happens to the temperature of this diatomic gas? Temperature increases. If temperature increases, pressure also increases. As soon as pressure increases, piston starts moving towards the right side. That's all, ma? And piston is moving up to which position? Piston is moving until the volume on the right side is becoming V0 by 8. Understood, no, ma? Initial volume was V0. So until its volume becomes V0 by 8, piston is moving towards the right side. This is the given data. Okay. Then what we are supposed to find out? Find the final pressure and final temperature on both sides of the cylinder. That is what I want to calculate. Clear, ma? First of all, if I study about gas on right side, Okay, ma? If I study about gas on right side, so all the walls, they are non-conducting walls, no? So heat energy is not flowing through this cylinder. Heat energy is not flowing through the piston also. So it means definitely this is an adiabatic process. If heat energy is not changing, it is an adiabatic process. So gas on the right side is undergoing which process, ma? It is undergoing adiabatic process. Okay. So initial volume is V0. Final volume is V0 divided by 8. That's all, no? Initial volume was V0 and it is compressed to V0 by 8, no? So final volume is V0 divided by 8. So what is the relation between pressure and volume? Okay. So P V power gamma is a constant. This is a relation for adiabatic process. Now substitute here. So therefore P1 V1 power gamma is equals to P2 V2 power gamma. That's all, no? So therefore let us substitute. So what is the initial pressure, ma? Initial pressure is P0. Initial volume is V0 power gamma. This is equals to final pressure, I don't know. Clear, no, ma? And what is the final volume, ma? It is V0 divided by 8 to the power of gamma. Clear? So V0 and V0, they get cancelled. So therefore what I will get? I will get P2 is equals to P0 multiplied by P0 multiplied by V0 has got cancelled, no, ma? So 8 power gamma. This is the value which I will get. Are you able to understand? And what is the type of gas present in the second piston? Monatomic gas. What is the gamma value of monatomic gas? 5 by 3. Substitute here. So therefore P2 is equals to P0 multiplied by 8 can be written as 2 cube, no? So 2 cube power 5 by 3. That's all, no? 8 can be written as 2 cube. 2 cube power 5 by 3. So cube and 3 will get cancelled. Cube and 3 will get cancelled. Now what is the value I have? P2 is equals to P0 power 2 power 5. 2 power 4 is 16. 2 power 5 is 32. Okay. So therefore P2 is equals to 32 times of P0. I got final pressure. Are you able to understand, ma? So this is the final pressure on which side? On both sides. That is the pressure on both sides, no? Because if piston moves up to some distance and piston is stopping, it means the same pressure is existing on both the sides. So therefore I say this pressure is present on both sides. Present on both sides. Okay, ma? Same pressure on both sides. So this is the final pressure. Okay. Then what he is asking, final temperature. Okay, ma? Final temperature on adiabatic process, how can I calculate? Pressure already I have calculated, no? And volumes also I know. Or I can calculate relation between temperature and volume also. So T V power gamma minus 1, this is a constant. This is the relation, no? So substitute here. So T1 V1 power gamma minus 1 is equals to T2 V2 power gamma minus 1. So initial temperature is T0, initial volume is V0 power gamma minus 1. Final temperature I don't know, but final volume is V0 by 8 power gamma minus 1. So V0 power gamma minus 1 and V0 power gamma minus 1, they will get cancelled. That's all, no? So therefore final temperature is how much, ma? Final temperature is T0 multiplied by 8 power 5 by 3 minus 1. Clear, no, ma? So T2 is equals to T0 multiplied by 2 cube to the power of 2 by 3. So 3 and cube will get cancelled. So T2 is equals to 4 T0. That's all, no? So this is the final temperature on which side? On the second side. That is on the right side. Understood, no, ma? So on the right side, final temperature is 4 times of initial temperature. Are you able to understand how we are calculating? And these calculations you should see. Okay? So make a note and you analyze them afterwards. Clear, no, ma? So once I calculate final temperature, now I have to go for the gas on the right side, no? Completed writing up to here? Right now. Okay? So Sima. So therefore, final pressure on both sides is 32 P naught, ma? And final temperature on the right side, that is in adiabatic process, is 4 T naught. Now we will calculate on left side of the gas, left side of the cylinder. Okay? Now on the left side of cylinder, can you say what is that process which is happening? Is this adiabatic? Is it isothermal, isochoric, isobaric? Huh? Isobaric. No, pressure is changing, no? Pressure has changed, no? My initial pressure is P naught, final pressure is 32 P naught. Then how it is isobaric? Huh? It is not as any specific process. All the three variables, they are changing. Pressure is also changing, volume is also changing, temperature is also changing. Okay, ma? So specifically there is no particular process here. Are you able to understand? Because no variable is a constant here. So therefore, pressure, temperature, volume are not constants. Anything is not a constant. Only number of moles of a gas is a constant. That's it. Are you able to understand? So therefore, if I use ideal gas equation, PV is equals to nRT. So can I say PV, what are the constants here? N is a constant, R is a constant. Remaining all the three, they are not constants. Okay? So therefore, can I write that PV by T should be constant? I can write like this. Pressure is not a constant, volume is not a constant, temperature is not a constant. Only N into R is a constant. So temperature also you take to the same side. Then I say PV by T is a constant because N into R is always a constant. No? Okay, ma? So therefore what I can do for two different conditions, I can write P1 V1 by T1 is equals to P2 V2 by T2. That's all. This is a very, very important relation. So this is a relation which we can use when no variable is a constant. All of them, they are changing. Okay. Now what I am supposed to calculate? T2 only, no? So calculate. So therefore T2 is equals to P2 V2 multiplied by T1 divided by P1 V1. Okay. Substitute all the values. Final pressure is 32 P naught, no, ma? And final volume is how much? This is very important. Okay, ma? Final volume is how much? V2 is how much? On this side. V2 is how much?
Sir, P1 V1 is
Huh?
V0 plus V0.
Abba.
Sir, P1 V1 is equal to P2 V2, just the volume is
Final volume is how much on the left side?
V0 by 8 is
V0.
V0 by 8 is 7.
See, ma, here what is happening? This piston has moved up to here, no? This piston has moved up to here. Okay? What is this remaining volume? This is V0 by 8. Clear, no? It means now this total volume will become volume on the left side, no? So if out of V0 by 8 is gone, what is this remaining volume? This is V minus V0 by 8. Or I will write here. Okay, ma? This remaining volume is how much, ma? It is V minus V0 by 8. Because out of total V0 by 8 is gone, no? Remaining volume is how much? V minus V0 by 8, which is equals to 7 V0 by 8. Up to which volume? Only this volume. Now this is the total volume of the left side, no? So V plus 7 V0 by 8. Evan arthamainda? Sima. So piston has moved up to here, no, ma? Piston has compressed up to how much volume? V0 by 8. So what is the remaining volume? Total volume minus V0 by 8. 7 V0 by 8. That is the volume of this much part of the cylinder. But piston has moved to this side, no? So this becomes my total volume on the left side. So V0 plus 7 V0 by 8. That is the final volume on the left side. So therefore, add it. So V0 plus 7 V0 by 8 multiplied by initial temperature is T0, no, T naught, divided by initial pressure is P naught. Initial volume is V0. That's all, no? If you do this calculation, you will get final temperature. That's all. Okay. So therefore, P0, P0, V0 and V0, V0, if they get cancelled. So what is the answer I will get, ma? So 32 multiplied by 8 plus 7, 15. 15 by 8 multiplied by T0. Clear, na, ma? 8 4s are how much? 32. So therefore it is 60 T0. That is my answer. Okay, ma? So final temperature on the left side is how much? 60 times of initial temperature. Right side. But on the left side, on the left side it is 60 T0. On the right side, it is only 14. Have you understood, ma, how we are calculating? So if you understand these problems carefully, you will understand how to identify which process is going on here. According to that, you have to do the calculation. Is it clear, ma? That's it. అది వాళ్ళని అడుగు బయాలజీ స్టూడెంట్స్ చెప్తారు. కప్పలు పోయలేదురా మీరు ఎప్పుడు? అప్పుడు క్యాన్సిల్ చేసినారు. ఏం బ్యాడ్ లెక్కలే, కప్పల గుడ్లకు పాపం. Okay, Sima. So next topic which we are studying is heat engine, ma. Very, very easy topic and very important topic. Sima. So heat engine example, bike. Bike is an example of a heat engine. Okay, ma? Listen very carefully. So in a heat engine, there are two important parts which we should remember. One is a heat reservoir. which is a continuous source of energy. For example, in our bikes, petrol will be there, no? Tank will be there, no? In which petrol will be present. So that you can call it as a heat reservoir, which is a continuous source of energy. Okay? So from heat reservoir, Q1 amount of heat energy, it tries to enter into the heat sink. What is meant by sink here? Atmosphere is called as heat sink. Are you able to understand, ma? So Q1 amount of energy is given by the reservoir, and out of that Q1 amount of heat energy, Q2 amount of heat energy is rejected into the atmosphere. Okay? And always Q1 is greater than Q2 in this condition. So therefore, what is the remaining energy, ma? Remaining energy is Q1 minus Q2, no? So that amount of energy will be utilized as useful work. Is it clear? Now let us see some example, ma. Let us take Q1 to be 100 joules of energy. Okay? Q1 is how much? 100 joules of energy is given by the heat reservoir. And heat sink, to the heat sink, that is to the atmosphere, how much energy is released? So, for example, 80 joules of energy is released. Okay? So, therefore, what is the remaining energy? 100 minus 80, 20. Only 20 joules of work is done by the bike or the heat engine. Are you able to understand, ma? So, this value is 100 minus 80, which is equal to 20 joules. So, this 20 joules is called as useful work. Are you able to understand? Is it clear, ma? So, what do you understand here? The point which we are trying to see is that the 100% of energy which is given by the reservoir cannot be converted into work. Definitely some energy should be wasted to the atmosphere or to the surroundings. Are you able to understand? Sima, when you run a bike, a lot of heat will be generated, no? What is heat? It is a form of energy, and that heat is given to atmosphere only, no? It means most of the heat is wasted here. Are you able to understand, ma? So therefore, it is not possible for a heat engine to run without rejecting heat to the sink. 100% heat should be given to the sink. Are you able to understand? So temperature of reservoir, I can call it as T1. Temperature of reservoir, I can call it as T2. So definitely I can say T1 will be greater than T2. Then only heat energy will flow, no? If temperature of reservoir is greater than heat sink, then only heat energy flows from the reservoir to the heat sink. Are you able to understand, ma? Now here we calculate a term called efficiency. Efficiency of heat engine. Okay, ma? So it means how effectively heat engine is utilizing the energy given to the heat engine. Are you able to understand? For example, we have many types of bikes, no, ma? Some bike will give only mileage of 60 km. Some bikes give a mileage of 70 km. That depends on their efficiency. How well they are utilizing the fuel which is present in them. Are you able to understand? How can I write efficiency? Efficiency eta can be written as work done per heat given by the reservoir. W divided by Q1. Okay, ma? So what is meant by W? W is nothing but work done by heat engine. Work done by heat engine divided by Q1. What is Q1? Energy received from reservoir. Are you able to understand? This is called as efficiency of a heat engine. Okay? So therefore efficiency can also be written as work done by heat engine is how much? Work done can be written as Q1 minus Q2 norma divided by Q1 value. So therefore it is 1 minus Q2 divided by Q1. Okay? So this is the equation to calculate efficiency of a heat engine. Okay? And by Carnot's theorem, so here I will make a note, ma. Write the note point here. Note point is that by Carnot's theorem, we can prove efficiency is nothing but 1 minus T2 divided by T1 also. This formula also we can use. Okay, ma? So efficiency is 1 minus Q2 by Q1 is formula. Efficiency is 1 minus T2 by T1 is another formula. This is in terms of heat energy received from the reservoir, and Q2 is the heat energy rejected to the sink. T1 is the temperature of the reservoir, T2 is the temperature of the sink. That's it. Okay, ma? And we are not going into much detail, ma, of what is meant by reservoir, what is meant by sink. There are very elaborate definitions. You need not to understand all those definitions, okay? Just remember up to here. So, Q1 is what? Q1 is energy given by reservoir. Energy given by reservoir. Q2 is what? Energy rejected to sink. Energy rejected to sink. So have you understood the bike and atmosphere example? No? Bike is a heat engine. Tank of a bike is a reservoir. Atmosphere is the sink. Finally, heat energy is given to atmosphere only. No? So atmosphere is a sink. Reservoir will be always at higher temperature. Sink will be always at lower temperature. Is it clear? That's it. Okay. Now Seema. So, question on heat engine. My heat engine rejects 75% of the heat supplied to the surroundings. Estimate its efficiency. So efficiency, what is the formula? Ma? So work done divided by Q1. This is the equation of efficiency. No? Or you can also write 1 minus Q2 divided by Q1. This also you can write. Okay. So what is Q2 ma here? Q2 is what? Q2 is the energy which is rejected to the sink. That's all. No? Q2 is energy which is rejected to the sink. How much energy is rejected to the sink? 75% of the heat is rejected to the sink. So 75 by 100, I can write 0.75 multiplied by Q1. I can write like this, no? I can write like this, no? 0.75% means 0.75. So this much of heat energy is rejected to the sink divided by Q1. So Q1 and Q1, if they get cancelled, how much I will get? 1 minus 0.75 is 0.25. So this is the fraction of energy which is called the efficiency of this heat engine. And if you write in percentage, percentage of efficiency is how much? Just multiply this one by 100. Okay. So therefore, how much it will be? It will be 25%. This is the efficiency of a heat engine. Okay, ma? So heat engine of highest efficiency has an efficiency of only 50%. In this world, if there is any engine which has highest efficiency, what is its highest efficiency? Only 50% only. Are you able to understand? Okay, ma? That's it. Okay, ma? So let us see this question. So, a motorcycle engine delivers a power of 10 kilowatts. So therefore, power delivered. Okay, ma? Power delivered is how much? 10 kilowatts. Or I can write 10 into 10 power 3 watts. This is what I can write. It is written in kilowatts. No, kilowatts is not the SI unit. Watts is the SI unit of power. In units and dimensions, all this you have studied, no? Apply చేయకపోతే ఏం లాభం ఇంకా? అప్లై కూడా చేయాలి. ఓకే, మీ నాయన నీ పేరు జ్యోతి అని పెట్టినారు, ఎప్పటి నుంచి సుబ్బక్క అని పిలుస్తాడు. ఏం లాభం? పెట్టిన పేరుతోనే పిలవాలి. ఓకే. So, and it is consuming petrol at the rate of 2.4 kg per hour. So, petrol consumption is how much? Petrol consumption is 2.4 kg per hour. So, units also we have to see very carefully. Are you able to understand? Then efficiency of the engine and rate of heat rejection we are supposed to calculate. And what is the calorific value? Calorific value is given as 35.5 megajoules per kg. Clear, no? Or I can write this one as 35.5 multiplied by 10 power 6 joules per kg. Are you able to understand? So this is the calorific value. What is meant by calorific value, ma? It means if I burn 1 kg of petrol, then I will get this much amount of energy. That is called as calorific value. And this value changes from material to material. Different fuels have different calorific values. Okay. So therefore, what he is asking, efficiency, so, and heat rejection, both he is asking. So efficiency, what is the formula for efficiency, ma? Work done per heat supplied. This is called as efficiency of a heat engine, no? How much work is done per what is the amount of energy which is received from the reservoir. Okay, or just you can say what is the heat supplied to the heat engine. That is called as this ratio is called as efficiency. Okay, so work done by the engine means what? Work done means what? Work done is nothing but power delivered by the engine. No, engine is giving this much amount of power. That is nothing but work done by the engine. Okay, make a note up to here. Okay, ma? Mark it. So here, what is meant by work done, ma? Work done is nothing but the power which is delivered by the engine. Okay. So engine is delivering how much power? 10 into 10 power minus 3. 10 power plus 3. Okay, ma? So here I will write down work done. Work done is nothing but 10 into 10 power 3 watts. This is the work done by the engine. Power delivered is nothing but work done by the engine. Engine is giving this much amount of work per every second. Watts, how I can write? Watts can be written as 10 into 10 power 3 joules per second. This is how I can write watts number. Watts is nothing but unit of power. Power is nothing but work done per unit time. So units and dimensions చాలా పర్ఫెక్ట్గా ఉండాలి మీరు. ఫస్ట్ చాప్టర్ అదే పెట్టేది, ఎందుకు? అది ప్రతి చాప్టర్లో వస్తుంది కాబట్టి. ఓకే, సో దిస్ ఈస్ ద వర్క్ డన్ బై ద ఇంజన్. ఇట్ మీన్స్ ఫర్ ఎవ్రీ 1 second ఆఫ్ టైమ్ it is giving how much energy, ma? Engine is delivering this much amount of energy, 10 into 10 power 3 joules of energy for every 1 second. Okay, then how can I calculate heat supplied? Heat supplied, how can I calculate? Okay, now we have to check for the units which are given. Are you able to understand, ma? Now see here, petrol consumption is 2.4 kg per hour. Okay, and calorific value is how much? Calorific value is 35.5 into 10 power 6 joules per kg. Now if you multiply petrol consumption with calorific value, see what is the unit you will get. So if I multiply these two, so what I will get? Kg by hour multiplied by joules per kg. This is what I get, no? Are you able to understand, ma? Already we have done one method on this one. So petrol consumption multiplied by calorific value. If you don't have any idea whether to multiply them, whether to divide them, what you have to do? Just try to multiply the units or try to divide the units and see what is the unit you will get. అర్థమవుతుంది కదా? So kg per hour multiplied by joules per kg. Okay, if I am multiplying them, kg and kg get cancelled, no? If kg and kg get cancelled, what is the unit I am getting? Joules per hour. Okay, now can you say what is meant by joules per hour? When you burn petrol, I am getting this much of energy per hour. That is the meaning of this one, no? It means this is nothing but heat supplied. Heat supplied. Okay, but I am getting value in hours, no? So you just convert that one into seconds. Is it clear? So therefore, heat supplied, how can I calculate? My heat supplied is nothing but petrol consumption multiplied by calorific value. Okay, petrol consumption is how much? It is 35.5 multiplied by 35.5 multiplied by 10 power 6 multiplied by calorific value. Oh, calorific value only I have written, no? It is equal to how much? 2.4. Okay, and what is the unit I will get? My unit I will get is joules per hour. This is what I will get. Okay, ma? So this is the heat supplied, or the heat which we are receiving from the reservoir when we are burning this much amount of petrol. Okay, but here what is the unit of work done? Joule per second I have, but here I have joule per hour. So convert this one into seconds. 1 hour is equals to how many seconds? 3600 seconds. So therefore heat supplied is how much? Heat supplied is nothing but, so 35.5 multiplied by 10 power 6 multiplied by 2.4 divided by 3600. Okay, ma? Are you able to understand? So once I do this calculation, now I can calculate efficiency, no? What is the formula for efficiency? This is the formula for efficiency, work done per heat supplied. Okay, so we will do here. Okay, ma? So therefore efficiency is equals to work done. So 10 into 10 power 3 divided by efficiency is heat supplied is how much? 35.5 multiplied by 10 power 6 multiplied by 2.4 multiplied by 3600. If you do this calculation, I will get efficiency of the heat engine. Are you able to understand, ma? And what is the value he gave? It is 42.2%. Okay, ma? So 42.2%. So you will get a fraction of efficiency, ma. When you multiply that by 100, you will get 42.2. Are you able to understand? That is the efficiency of a heat engine. Okay. Now, one more question also he is asking, no? Second question is also there. What is the second question? Heat rejection. What is the amount of heat which is rejected? That one how can I calculate? Heat rejected, how can I calculate, ma? Heat rejected is nothing but heat rejected. What is the formula of heat rejected? Heat rejected is nothing but Q2, no? the amount of energy which is rejected to the sink. Okay, ma? So Q2 value, how can I calculate? Q2 value is Q1 minus W. This is the amount of heat rejected. Q1 is the heat supplied. That already we have calculated here, no ma? So 35.5 multiplied by 10 power 6 into 2.4 divided by 3600 minus, what is the work done? Work done is this much, 10 into 10 power 3. So just to do this calculation, you will get the amount of heat rejected. Okay, ma? So these values, I hope you can do, ma. That's why I'm not doing. So 13.7 kilowatt. Or you can write 13.7 kilowatt. Clear? That's it. Okay, ma? Now see. So, heat engine receives 50 kilocalories of heat from the source. That is the data which is given, ma. So, it is receiving 50 kilocalories from source. Are you able to understand? So, what is the meaning of this one? So, heat received from source. That is the meaning of this one, ma. So first of all, you have to identify which one is Q1, which one is Q2. ఇక్కడ వీడు Q1 ఇస్తున్నాడా, Q2 ఇస్తున్నాడా, అది ఐడెంటిఫై చేయాలి ఫస్ట్. ఓకే, సో ఇట్ ఈస్ రిసీవింగ్ 50 kilocalories means what? It is he's received from the reservoir only, no? Okay, and what is its value? Its value is equals to 50 kilocalories. Okay, ma? So for every one cycle, it is receiving this much amount of energy. And what is the efficiency? Efficiency multiplied by 100 is nothing but 20%, ma? Efficiency always you will get in fraction. And that efficiency, if you multiply by 100, then it converts into a percentage. Okay, so therefore what is the efficiency? Efficiency is equals to 20 by 100, which is equals to 0.2. That is the efficiency of this engine. Are you able to understand? So determine the work obtained from the cycle. Work obtained from the cycle means what? Work done by the engine. It means for every one cycle, how much work it is able to do. That is called as W. Okay, ma? So therefore, what is the equation? Efficiency is equals to work done divided by heat received from the source, reservoir. That's all. No? So therefore, work done, how can I calculate? Work done is nothing but efficiency multiplied by the energy received from the reservoir. Okay, efficiency is how much? 0.2. And Q1 value is how much, ma? Q1 value is 50. So therefore, 5 2s are 10. 10 kilocalories of energy is done by the engine for one every cycle. Okay, it is receiving how much energy? 50. But it is doing how much work? Only 10. It means how much energy is rejected to the sink? 40. Okay, no? So heat rejected is how much? Heat rejected. What is the formula? This is equals to Q1 minus W. This is the heat rejected to the reservoir. Sink. So therefore it is 50 minus 10, which is equals to 40 kilocalories. That is our answer. Understood, no? Very, very simple. Okay, Sima. So reverse heat engine. What is meant by reverse heat engine? That we will study afterwards. First of all, we will see second law of thermodynamics. So there are many statements of second law of thermodynamics now. So Kelvin statement, Clausius statement. There are some 3 to 4 statements are there. Each statement given by different scientists. And what is the basic meaning of all these statements is that this is the meaning of it. Second law of thermodynamics. So total heat energy cannot be converted into useful work. Okay, ma? This already we have studied at the starting of the topic, no, ma? Total heat energy, you cannot convert that one into useful work. Some of the energy must be rejected to the sink. So this is the meaning of all the statements of different statements given by different people. Are you able to understand? So therefore, some energy must be rejected to sink. Okay, so the heat engine with highest efficiency, has an efficiency of only 50%. So what is the meaning of this one, ma? So heat engine's efficiency cannot be 100%. Okay, because if efficiency is 100%, what is the meaning of it? Which means the total heat energy is converted into work. That is called as efficiency 100%. But the heat engine in the world which is having highest efficiency, it is having an efficiency of only 50%. For example, yesterday we studied that a bike is also a heat engine. The bike which we ride is a heat engine. But that has efficiency of only 20 to 30% only. Are you able to understand? So if a bike's efficiency will become 100%, we will get a mileage of nearly 250 kilometers per 1 liter of petrol. Are you able to understand? We are getting only 50 to 40 kilometers only, no? What is happening to the remaining energy? It is lost as heat energy. You should have studied global warming, no? So the heat energy which is received with the bike, it is released into the atmosphere. So temperature of the atmosphere will be continuously rising. Are you able to understand? So some of the heat must be rejected to the sink. And here who is the sink? Atmosphere is the sink. Are you able to understand? Now, yesterday we have studied heat engine, no? Heat engine. What is the heat engine? So here you will have a reservoir. Okay, ma? And from the reservoir we will receive how much energy? Q1 amount of energy. Okay, ma? Some of the work will be done as useful work, and remaining heat energy will be rejected to the sink. This is what we have studied, no, ma? So what is the amount of energy which is rejected to the sink? Q2. Okay. So then what is the amount of useful work done? Q1 minus Q2 is equal to W. This is the amount of useful work which is done. So this is the concept of an heat engine. And what is the temperature of reservoir? Temperature of the reservoir is T1. Temperature of the sink is T2. And definitely T1 must be greater than T2. Temperature of reservoir must be greater than temperature of the sink. Then only heat energy naturally flows from reservoir to sink. Heat energy eppudu ela flow avutundi from hotter body to colder body without spending any energy. But now we are studying the second type of heat engine which is called as reverse heat engine. Okay, ma? So what is meant by reverse heat engine? I want to take heat energy from cooler body. I want to take out heat energy from cooler body and give to hotter body. Arthavatunda? Naturally heat flows from which body to which body? Hotter body to cooler body. Here you need not spend any energy. Mere energy spend cheyalsina avasaramu ledhu, external energy is not required. But what I want to do is I want to change these directions. Previously Q2 was entering into the sink, no? Now Q2 direction will become like this. This is the direction of Q2. Okay, what do you understand? It means heat energy is taken from the sink. This is a cooler body, no? I want to take heat energy from cooler body and give to hotter body. It means here also my direction of reservoir heat energy will change. Are you able to understand? If these two will change, definitely this direction also will change, no? So therefore here what I will write, here the direction is inside. Okay, I have to do some external work. Now W direction is changing. What is meant by W direction is changing now? We have to do some work. Are you able to understand? And that work done is how much? Again it is equals to Q1 minus Q2. Are you able to understand what is happening? So therefore, to take out heat energy from a cooler body and give it to hotter body, we have to do some external work. Because heat naturally doesn't flow from cooler body to hotter body. We have to do some work. Okay, ma? So this work is called the external work which we have done, or the external energy which we have spent. So this is the concept of a reverse heat engine. So can you say example of reverse heat engine, ma? Refrigerator is an example, no? So in refrigerator what is happening? We are taking out heat energy from inside of the refrigerator and we are giving that heat energy to the surroundings. Are you able to understand, ma? It means heat is received from cooler body. Heat is taken from cooler body and heat is given to hotter body. Naturally this cannot happen, no? So we are supplying current to this one. Electrical energy we have to supply. So this is the electrical energy supplied. This is the inside of the refrigerator and this is the surroundings. Is it clear, ma? So that is the concept of a reverse heat engine. So write down, draw this diagram. Completed, ma, this one? Huh? So see here I will write. So heat naturally flows from hotter body to colder body. hotter body to colder body. Okay, ma? But to remove heat energy from colder body to hotter body, we have to supply or we have to do external work. Okay, ma? And that external work is nothing but W. Directions, you are able to understand, Amma, what is happening? Okay. So therefore, so here I will write down. Okay. So Q1 plus W, Q2 plus W will be equal to Q1. Okay. So therefore, W is nothing but Q1 minus Q2. Okay, ma? So the work which you have done, that also enters into the sink, and Q1 amount of energy is also released into the sink. Okay, ma? No, this is not the direction. Make a note up to here. That is how nature is behaving. మనం స్ట్రైట్గా నిలబడి ఎందుకు నడుస్తామంటే భగవంతుడు అలా సృష్టించినాడు అనమాట. కోతులు అలా నడవు కదా. That is how nature is behaving. Okay, ma? We don't have any logical reason for that. 100% of heat energy we cannot utilize. Some of it must be rejected into the reservoir, sink. ఒకసారి ఎలా చేస్తావో చూపిస్తే నేను కూడా చూస్తాను రా. Okay, ma? Now see. So therefore, see, ma. So see here what we have written Q2. What is Q2 here? Q2 is the energy which is taken away from the sink. What is W? External work done. So these two added up and it will give Q1. And what is Q1? Q1 is the energy which is rejected to the reservoir. Are you able to understand, ma? So therefore W is equals to Q1 minus Q2. Okay. Now here in this reverse heat engine, we have to study about a very, very important parameter which is called coefficient of performance, ma. So questions can be given on this term called coefficient of performance of refrigerator or heat engine. Okay. So the term which we are studying is coefficient of performance. Okay. So what is meant by coefficient of performance? It is represented by the term beta. Okay. Sometimes it is represented by alpha also, but in most of the books it is given as beta. So beta is nothing but, so the heat rejected to, no, not heat rejected. So heat taken out of sink per amount of work done. Okay, ma? So this ratio is called as coefficient of performance beta. Okay, ma? It means this is the amount of work which you are doing, no? For this amount of work, how much energy you are able to take out of the what you called sink. Are you able to understand, ma? Heat energy we are removing from sink only, no? So how much energy you are removing per the amount of work which you are doing. That is called as coefficient of performance. So if beta value is greater, what is meant by beta value is greater? It means that refrigerator is a very good efficient refrigerator. It means for a small energy, it is able to remove huge amount of energy. For example, if you go to buy a refrigerator, there you will have star ratings, no ma? So 1 star, 2 star, 3 star, 4 star, 5 star. Ratings kanipistayi kada meeku. What is the meaning of that ratings? Rating, if it is good, it means that work done will be very less and heat received will be very large. That is called as higher rating refrigerator, no? Current bill chala takkuga vastundi. Current bill will be very lesser for 5-star rated refrigerator. Okay. And who decides that rating? This decides the rating. How much heat energy you are able to remove per the amount of energy supplied. Energy supplied is nothing but electric current. Are you able to understand, ma? So therefore, heat taken out of the sink is nothing but a Q2, no? Okay. And what is meant by work done? Work done is nothing but W. So therefore, Q2 divided by W. W again, how can I write? W, how can I write, ma? So Q2 divided by W can be written as Q1 minus Q2. I can write like this also. Are you able to understand? So this is the equation to calculate the coefficient of performance of a reverse heat engine or a refrigerator. Okay? Make a note up to here. Okay, ma? Now, by Carnot's cycle. Okay, ma? By Carnot's cycle. What is meant by Carnot cycle? We will study later. By Carnot's cycle, okay, ma? Efficiency of a heat engine can be written as 1 minus T2 divided by T1, or also you can write efficiency is equals to 1 minus Q2 divided by Q1. I can write like this also. Are you able to understand? So, what are the different formulae for efficiency, ma? One formula is 1 minus T2 by T1, another formula is Q2 divided by Q1. So this beta equation, I will try to convert beta in terms of efficiency. Okay. Now let us see how we can convert this one. Sima. Beta can be written as Q2 divided by Q1 minus Q2. No? So divide every term by Q1. Okay, ma? So dividing every term by Q1. Or just you can write a beta is equals to Q2 divided by Q1 divided by Q1 minus Q2 divided by Q1. I can write like this. Are you able to understand? So therefore, what it becomes, so Q2 divided by Q1 divided by 1 minus Q2 divided by Q1. I can write like this also. Are you able to understand? So just you can say that we are multiplying and dividing by Q1. Or you can say everything is divided by Q1. Both are same. Okay. Then this is the format of equation which I got. Q2 by Q1 divided by 1 minus Q2 divided by Q1. Now see. So here, what is Q2 by Q1? Q2 by Q1 is nothing but 1 minus efficiency, no ma? So look here. Efficiency is 1 minus Q2 by Q1. So Q2 by Q1 value? Q2 by Q1 is nothing but 1 minus efficiency, no? Take this value and substitute there. So therefore, beta is equals to Q2 by Q1 value. I can write 1 minus efficiency divided by 1 minus Q2 by Q1. 1 minus Q2 by Q1 is nothing but efficiency. Clear, nama? Divided by efficiency. So this is the relation between coefficient of performance and efficiency of a heat engine. Okay, ma? So all these relations you are supposed to remember. So this is one equation of efficiency. This is another equation of efficiency. Okay, and this is the equation for relation between beta and efficiency of a heat engine. Are you able to understand? So if you look at these two equations, from these two equations I can write one more equation. I can also write T2 by T1 is nothing but a Q2 divided by Q1. I can write like this also. Are you able to understand? Right now. So the last concept which we are studying is Carnot's cycle. So what is Carnot's cycle? So this is a cycle which was designed to check what can be the maximum efficiency of a heat engine. Okay, ma? And it was proved that only in Carnot's cycle only we will have maximum efficiency. Okay, and this is a cyclic process, no? Initial states are P1, T1. Final state is also P1, T1 only. And in the process we are doing one isothermal process, one adiabatic process, another isothermal process, another adiabatic process. So Carnot cycle consists of basically two isothermal processes and two adiabatic processes. Okay, ma? So this derivation we are not doing here. We are just studying the result of this. So result is that, so Carnot's cycle has maximum efficiency, and it is equal to eta is equals to 1 minus T2 divided by T1. Okay, ma? This is the final result which we understand when we do this cycle. Okay, so there can be many processes in which I can do work with the help of heat engine. Ma? Heat engine use chesi chala rakala processes tho nenu work cheyochu. But only in this process, efficiency will be maximum. And what is that maximum efficiency? This one. Eta is equals to 1 minus T2 divided by T1. Are you able to understand? Previously, we studied efficiency of a heat engine. No? Efficiency of a heat engine is how much? 1 minus Q2 divided by Q1. Do you remember? While studying heat engine, we studied this one. No? So efficiency of a heat engine is 1 minus Q2 divided by Q1. Now efficiency in the case of Carnot engine in terms of temperature is 1 minus T2 divided by T1. Now what is T2 here? T2 means temperature of sink. Okay ma? T1 means what? Temperature of reservoir. Are you able to understand? Now see, when you look at this equation, efficiency is equals to 1 minus T2 divided by T1. To have maximum efficiency, what can be the values of T1 and T2 ma? Efficiency I got 1 minus T2 divided by T1, no? To get maximum efficiency, T1 should be how much? T2 should be how much? Questions will be asked on this topic. Are you able to understand? Can you say? T2 ఎంత ఉండాలి, T1 ఎంత ఉండాలి for to get efficiency to be maximum? ఆలోచించండి. Sima. So here consider T1 is very large. T1 is in denominator, no? T1 ekkada undi ikkada? T1 is in denominator. If denominator is very large, T1 means temperature of reservoir, no? It means if temperature of reservoir is very large, then T2 by T1 will become almost 0, no? T2 by T1 will become almost 0. So consider T2 is 30 degrees, T1 is 1 lakh of degrees. అర్థమవుతుందా? So let us consider T2 is equal to 10 degrees Celsius, T1 is equals to 1 lakh of degrees Celsius. 10 by 1 lakh? Very less, no? Almost you can say 0. Then efficiency will be how much? Efficiency will be 1. Efficiency 1 means what? 100% efficiency. Are you able to understand? So to get 100% efficiency, these are the two factors which should be satisfied. Temperature of a sink should be very, very, very less. Sink temperature, for example, you take the example of a bike. Okay ma? Sink temperature means temperature of atmosphere, no? Okay ma? So if atmosphere temperature is very less, then mileage of the bike will be greater. Are you able to understand? Similarly, T1 should be very large. It means this bike should be operating at what temperature? Bike should be operating at 1 lakh of degrees Celsius, which is not possible. Are you able to understand ma? So reservoir should be at a very large temperature, sink should be at a very less temperature. Then efficiency will become maximum. Both are not possible. Are you able to understand ma? So if temperature of sink is minus 273, that is the least possible temperature which is possible, no? So if temperature is minus 273, nothing will happen in the universe. No, every function will stop. Okay? And temperature of the reservoir is very, very, very large. Heat engine will melt away, no? At 2000 degrees Celsius or 3000 degrees Celsius, any heat engine will start melting. So that is also not possible. Okay, ma? It means that efficiency of a heat engine can never be 100%. That is what we understand by doing the cycle called Carnot cycle. Are you able to understand? So write down the note points here. Note point is that, clear ma? So for efficiency to be 100%, for efficiency to be 100%, okay ma? So temperature of a sink should be very small. Temperature of a sink should be very small, and temperature of reservoir should be very large. Should be very large. Both are not possible. Both are not possible. Okay ma? Therefore I say, efficiency can never be 100%. It is not at all possible to construct any heat engine with an efficiency of 100%. Understood, no? Reason we have understood, no ma? 1 minute ma. Hello? Huh? Adema, efficiency formula is 1 minus T2 by T1. And efficiency depends on these two factors, no? And this will become maximum only if T2 is very small and T1 is very large. Then only efficiency will become maximum. Both are not possible. Least temperature is not possible. Highest temperature also not possible. Okay? See, my people in foreign countries, they will be very tall, very strong, no? Americans mallaga bhumiki touch ayi untara? Have you seen American people? Or people in New Zealand, Australia, ఒకరు ఎంత ఉంటారు? 6.2, 6.3 ఉంటారు. ఎందుకంటారు అట్లా? చెప్పండి, దీని ప్రకారం చెప్పండి. వాట్ ఈస్ ద రీజన్? హ్యూమన్ బాడీ ఈజ్ ఆల్సో హీట్ ఇంజన్, నో? Human body is also heat engine. So by looking at this example, how can you say why these people are very tall and very strong? Because T2 is very small for them. The area in which they are living, temperature of the atmosphere is, that is temperature of the sink is very small. So automatically their bodies will have higher efficiency from birth itself. Are you able to understand? So a cool climate lo peragatam valla, automatically they will become very tall and very strong. Are you able to understand? While we are attached to the grounds only. That is the reason. Understood no? Why efficiency will be maximum? Cannot be maximum. Okay? So make note. So efficiency can never be 100% only because of this reason. And this we understand by Carnot cycle. Okay? Right. Okay, ma? So see, ma, calculate the thermal efficiency of a Carnot's heat engine working between ice and steam point. What is meant by ice point and steam point, ma? 0 degrees Celsius and 100 degrees Celsius. That is the meaning of this one, no? So efficiency is equals to 1 minus T2 divided by T1. So 1 minus T2. T2 means what? Ice temperature or steam temperature? Ice temperature. T2 is lesser temperature, no? T2 is always temperature of sink. Sink means always it will be at lower temperature. Okay? Viranam okate kada apply kuda cheyali. Okay ma? So T2 means ice point. And what is the ice point? 0. But T, capital T written over here, what is the meaning of it? You have to convert into Kelvin. So 0 degrees Celsius is nothing but 273 Kelvin, no ma? Divided by T1. T1 is 373. T1 means steam point. Water boils at how much degrees Celsius? 100 degrees Celsius. 100 degrees Celsius is nothing but 373 Kelvin. Okay? So if you do this calculation, I will get the efficiency of this heat engine. Okay? So how much it will be? 22.2681. 0.2681. Okay? And percentage of efficiency? 26.81%. That is the efficiency of a heat engine. Okay, ma? So when temperature of sink is 0 and temperature of reservoir is 100, then heat engine will have this much amount of efficiency. Very less. 26 is very less, no? Okay.